Welcome to week 5, lecture 2, or the last, oh, my mic's all the way over here. Better. And the music's got to go. We're all over the place. Okay, welcome to week 5, lecture 2. Sorry about that. Or as I was saying, the last lecture before the midterm break. Can you believe we're almost halfway? Exciting, scary, sad. If you look back to week 1, if you take a moment right now to look back to week 1, I hope you can all appreciate, if 1511 was the first time that you'd been programming, that you can recognize how much you've learned. I mean, we were literally talking about how to make a variable, how to write main, and now all of a sudden you're writing these sort of complex programs just in a few weeks. So sure, take a moment to congratulate yourselves, excuse me. Okay, first thing I wanted to talk about before we get into today's topics. Let me fix this up. So as you'll know, we have the help sessions now. Okay, this is a bit off. There we go, everything's got to be perfect. Okay, as you know, we have the help sessions now, and the help sessions can get quite busy, especially around the assignments. This is probably maybe one of your first few courses that have a busy help session at UNSW, so you maybe not have seen it yet, but the help sessions will get really busy. So what we have, I think Tom, the course admin, built this. I think the first time it was used was last term, and this is now the second time we're going to use it. We've made a few adjustments. So basically, what is this? This is called Hail. Last time was the first time. Pretty exciting. I've just sent a link to it in the chat. The idea is help sessions get really busy, but sometimes you really just need access to help. So there's basically everyone gets some limited opportunities to these fast passes, which will essentially fast track you to get help in the help sessions. So you go to this URL, you log in, you can view the upcoming help sessions that are scheduled throughout the course, right? So you might be thinking, I'm really stuck on this problem. I know if I'm going to go to the help session, I'm just going to be waiting for a while, but I really just want to get unstuck. I've not used a fast pass before. So you can sign up, and there's a limited number of fast passes per help session, and then I think you get access to a limited amount of fast passes per course. The exact specifics of all this, I think we sort of adjust it. Tom probably has some more details, for example, bubbling on how many you get access to, how long before the session you can apply it, all of this stuff. Excuse me. So yeah, you can only have one at a time. Am I missing anything? So basically, I'm not going to do it, but you can just click sign up. It's like Disneyland. Yep, the fast pass system that they used. Except we don't make you pay for it, right? So we could. And this is for both online and in-person sessions. Can I click one? What's it going to do? There you go. So I can just accept that, and then I'll get a fast pass for that session. Oops. Was it meant to do that, Tom? Whatever, just refresh, it's back. Okay, so yeah, that's worth reiterating. These aren't necessary to get help. There's just a limited amount of them so that you can get sort of more guaranteed and quicker help, hopefully, at the help session. Yeah, I shouldn't do that. That's okay. Okay, am I missing anything on Hail? I'm sure if I have, Tom will follow it up in the chat. Otherwise, it's pretty straightforward. Look at the time, look at the date, and please, if you're getting a fast pass for a particular session, make sure you know that you can attend it and that you will attend it, and we should be good. Cool. Yeah, let us know if you have any issues. As always, nice little nifty process we've got going on here. Thank you, Tom. Yep, I'm sure Tom's going to go now and figure out what went wrong with that refresh. Okay. Oh yeah, okay, cool. And you can cancel them. I'm sure that'll happen to a few of you. You'll be really stuck on something. You'll get a fast pass, and then you'll sort it out, and then you won't need it. It's a good question. I don't think it is linked on that. I'm just looking at the course site now. If it's not, it's probably worth us doing. Unless it's under help sessions. I don't think it is. Not a bad idea. We'll take a look at that. Thank you, Matthew. All right. Okay. Cool. All right, let's get into it. So today, what are we talking about? One of the interesting things about today's content is that we're not really introducing any new concepts. We'll be introducing some new syntax and things like that, but no new fundamental concepts, which is pretty cool. However, having said that, what we're doing is putting some concepts together that will be really useful throughout the rest of the course and your programming career. So Nicholas, you can watch the lecture at any time. Yeah, of course. Okay. So, as always, the lecture code is available here, and I know Patrick or Tammy is going to put the URL into the live chat. All right, so let's do a little recap on structs and pointers, because today what we're going to be doing is putting these two concepts together. So, what is a struct? A struct is a custom data type. In the custom data type, we can have a collection of properties or members of the struct that model or relate a structure of data in a single variable. So we're creating a custom data type. So for example, a user could have a username, an email address, a user ID, things like that. And if we, okay, got a bit of a cough, sorry. If we want to access the members of a struct, we use a period. So we can say, my struct.username, and that will access that username variable. And I'll do a little recap in some code even in a moment. So far we've had variables which can store values, and that could be, for example, a struct. These slides aren't the same. I was modifying them a bit last night and this morning, Gabe. So they're slightly different. I'll update these ones after the lecture. But they're similar. So we've been able to have these variables which store values, and we have variables which can store pointers to a value. And we're pretty happy with that. But one of the cool things about pointers is that rather than making us copy around a value itself, they allow us to copy a pointer to a value or a reference to a value. Now, if you think about it, and if you're thinking sort of ahead, you might think, well, because structs can store multiple pieces of data, they could get larger than just like an integer or a double or a character, right? Because you could have 10 things in a struct, and we don't know how big those things are. So you can imagine that a struct could get fairly big. So what if I want to use pointers with structs so that I can just store a reference or a pointer to a struct, so that when I need to pass my structs around, I don't need to copy a big chunk of data, which is what I would be doing if I just pass a struct around. Does that make sense? Whenever we pass data to a function, for example, we need to copy that data. And if the data is big, the copy is expensive. It takes a lot of time because we have to go off to the operating system and we have to say, please, Mr. Operating System, I need enough data to store a struct, and the struct might have 50 things in it. That's quite a bit of data. And then the operating system says, hold on, 30 other programs have asked me for memory. Give me a second. And then it goes off and gives you the data. So it's expensive. So what if we wanted to store a pointer to a struct so that we create the struct once and then I can just pass references to it? So let's sort of look at this. Let's make a struct and then store a pointer to that struct and look at what we have to do in order to access it. Okay, so let's go to VLab. Whoops. So let's just do a really quick structs recap right now. Okay, so I've got a file here called structs recap. Okay, int main void hash include standard io.h. Leave me alone. Okay, return 0. Now what I'm going to do, something I don't think I've done in a lecture so far, we can store a struct called coffee, and in the coffee we might have a character array called the name, and it might have a price. So we need to define max string len, let's just call it 20, that's fine. All right. So I think this is something we haven't done yet, but we can have a string in a struct just like this, character array with the maximum amount of characters it can store, and a price. Okay. So I can make this, called my coffee. And I need to be able to put, access the members of the struct to put some stuff into it. So I can pretty much go my coffee.price is equal to $2.50. We all know coffees aren't costing that much at the moment. That's okay. Now, strings are a bit different when they're declared like this. We need to use string copy. So I think that's coming from strings.h. And I can just do a string copy like this. And I can do my coffee.name, and I'm going to copy in maybe an espresso, something like that. So this is how you actually assign a string to a string in a struct. I think it's strings.h, I'm pretty sure. All right, and then what we can simply do is just print this. %s costs long float. Oops. I can put a little $sign here, comma. What's first? My coffee dot name, and then my coffee dot price. Okay. So DCC structs. No. Yeah, that should be fine. Dash header program. Okay, we've got an error here. I've forgotten my semicolon after the struct. This is what it's telling me here. Expected a semicolon after the struct. I mean, that always makes sense. Okay, maybe it is string.h. Sorry about that. Yeah. Okay, let me just put a new line here to make it nice and pretty, but we can sort of see that we get what we wanted pretty much. And I can do something like this, I think. It's really annoying. To get a nice little printout. So the purpose of this is just to really quickly recap that we can define these structs and we can access the members of the structs with the period. Cool? Any questions on this so far? Strings are cool? Yeah, they are cool. Makes sense? Cool. Awesome. All right. Nicholas, this is just capping the number of decimal places of my float to 2. That's why it's just 250 now, rather than 2500000. Okay. Let's make a new file. Structs parsing.c ampersand. I'm going to actually copy all of this, paste it in here. So they're both going to be available. And I want to show you something. So let's say we make a function now that prints a coffee. So its job is to take in a struct coffee parameter and print it out. So how do we do that? Well, we can just call it print coffee. What's the parameter going to be? It's going to be a struct coffee. Yeah, and then my coffee, for example. Now, what's going to happen, and this could basically just do that print, and then we're just going to call this here. Print coffee, my coffee, and then this can basically just go away. Structs parsing, and then I'm going to do, let me just start off with that. Okay, cool. And then I'm going to run the program. And we should just see if that works. It does the exact same thing. But what I want to do is take a moment here to discuss what's actually happening. So we make a struct, assign it some values, and then we pass it to a procedure, a void function. Our function accepts the struct as a parameter and does something with it. In this case, it prints it. All right, so I think so far here, again, we should be pretty happy. But let's think back to parameters and arguments and things like that. If I changed, that looks like it's not. If I changed my coffee price, will it update this struct down in main? And print coffee is a procedure. Why is it a procedure? In this case, it returns nothing. It's just doing something. So think back to our variables that we pass around as parameters. If I do this, if I change, my coffee.price, for example, excuse me, I got a cough. If I do that, is it going to change down here in main? So if it accepts a struct, does that mean it automatically accepts all the variables inside the struct? So yeah, the whole struct is getting passed in. So the coffee, the price, anything that's in the struct gets bundled up and passed in. Same thing, no, print coffee is working with a copy of my coffee, not the original, is what Daniel Barry says. And I can't agree more, which is why the answer is no. So if I change the price here, what we have here is a copy of the struct. It's a copy of the struct. Okay? When we have a parameter in C or an argument, yeah, it's a clone. It's making... This has asked the operating system for more memory. Are we all happy with that? Just the same if it was an integer. Exactly the same if it was an integer or a character or a double or anything that's a built-in data type. Excuse the cough, I apologize. Because of the stack, I think. Basically, right, it's making a new stack frame, and on that stack frame, it's allocating enough memory for a character array of 20 length and a double. Yeah, arrays are different, Gabe, because arrays, when we have a reference to an array, all we pass in is the memory address of where the array starts. So arrays will update because you are passing in, you can think of it as like a pointer to the array. So Daniel's saying, so it copies it from one stack frame to another. Absolutely right. It takes the data from the main stack frame, copies it over onto the print coffee stack frame. But like I said before, allocating memory is expensive and we don't like to do it if we don't need to. In this print coffee procedure or function, do we actually need a copy of the data? Is there any reason that we can think of that we actually need a copy? Was it worth that hassle of allocating the memory? Nikhil saying no. No, we don't need a copy. So why have we spent all that effort copying it? That's not good programming, right? That's wasted computation cycles, right? Yeah, it's too much effort. It's unnecessary. So Gabe is saying, well, why are we just doing printf without a function? The point, we could be doing other things here that we want to be doing, right? This is what we should be wanting to do. We want to have a procedure to print it, but we don't necessarily need to copy it. So what can we do? Can anyone tell me? I mean, maybe it's obvious to some of you, but if only we had some way to not pass the full struct, to pass some sort of reference to the struct or some sort of, yeah, exactly right. Exactly right. We can pass a pointer to the struct. Exactly right. Exactly right. Okay. So why don't we do another little duplication? Gedit structs pointers.c and an ampersand, paste it in. Print coffee, okay. Now, let's delete those comments and delete this comment. How do I do this? Yeah, pointers are overpowered. I want to pass in a coffee still, but rather than pass in a full value of a coffee, I just want to pass in a pointer to a coffee struct. There's two I's in the title. Oh, that's okay. You get the idea. That's it. With that one tiny change, what I'm telling the compiler is don't make a copy of the struct coffee. Pass in a pointer to a coffee. Now, we have a bit of a problem. I can show you the problem. Oops. Structs pointers.c -o program. What have I just done? That's gedit. Okay, I'll move structs pointers.c to structs pointers.c. DCC structs pointers.c -out to program. Oh. And we have some errors here. We've got a problem. Who can spot the problem? The problem is, and I'm not really waiting for you to answer, the problem is my coffee is no longer a struct. So I can't do my coffee.name because my coffee is not a struct. Agreed? All right, so what do we need to do? What we can simply do is say, well, if my coffee is a pointer, we can get the value of the pointer, right? We can follow the value of the pointer. And then we need to give it brackets to say, go evaluate the value of the pointer and then access the name. And we'll have to do that twice. So go dereference the value, the pointer. Yes, let me give you access to the lecture code. Thank you, Patrick. Let me dereference my pointer to the struct, and then I'll be able to access the name. And if we do that, what did I do wrong? Did I not save it? Oh, this is still structs pointers here. File, save as. Yeah, okay. Oh. I didn't reopen it. Yeah, replace it, leave me alone. Clear this. Okay, what's this problem? Okay, yep. And well, we can already see that those errors went away, so that's fine. And then what I want to be doing here is not pass in the actual whole struct, because again, that's not the address of a struct or the pointer to a struct. Get the pointer of the struct and pass that in. And if I do all of that, it compiles my problem, and I run it, and I get the exact same output. And I mean, it's sort of hard to see, right? Because programs just run really quickly anyway. But this is no longer copying coffee. Coffee and copy rhyming, it really annoying. It's passing it. You mean you can see. Pass it in as a pointer. Yeah, it's worth it. If imagine you had lots and lots of structs with lots and lots of data, we're using much less memory. Exactly right, Bonrick. Exactly right. Exactly right. Yep, so remember, I know you've got it bubbling, but the ampersand says, give me this variable, this value, and get the address of it. Turn it into a pointer. And then pass the pointer in. The function accepts a pointer. We can dereference the pointer and then access the members. So this is one thing that pointers are commonly used for in C. Now, we could stop here. This is enough. With this information, so we actually, sorry, I feel like I'm yelling. We actually unlock a few things here, a few powerful things. Number one, what do we unlock? We don't need to copy the data. We've already spoken about that. So we're using much less computational cycles. Number two, we're passing in pointers to structs. So I could, make a function, I could say update the price of a coffee. I pass it in and it increases the price. Because I've got a pointer to it, then it will update down here in main. Just like that's what we knew about using pointers in general. Prison's Mike's saying, why can't we just use printf for this? Let's say I wanted to print my coffees many times. Like every time someone makes a new coffee, I want to print it again. What's easier to type? Just make a procedure to print the coffee, or to retype this whole printf line? Then what if I had something like if, string compare my coffee, I could have lots and lots of extra things in my procedure that I wouldn't want to be rewriting every time I print it. So, I could do something like if the price is greater than $2, I also want to printf, you know, do you need a tax receipt? You know, statement, whatever, \n, right? Okay, if I want to print it 3 times, do I really want to put these 3 lines everywhere? So this is just an example, that's right. But oftentimes the reason we have functions and procedures is to reuse, you know, to decompose and reuse these lines. And if I do this now, you'll already get the idea that I wouldn't want to put these 3 lines down here, and down here. Okay. Yeah, that's exactly right. If we had types of milk and all this, there's a whole, I mean, you can already see something like this is pretty useful. All right. So like I said, we could stop right here. This is really cool. We're happy. However, this is, yeah, and you're keeping main to a bare minimum. Exactly right. However, this pattern of passing a pointer to a struct is so common that the C language designers thought, you know, okay, in a few decades, the COMP1511 students are going to be writing this assignment. They're going to be tired. It's, you know, all this. I feel bad for them. This syntax is pretty ugly, right? That's what they're going to say. And I know the students will forget the brackets. And then this looks like they're trying to dereference the whole name. And if you do that, that's going to not compile. They felt sorry for you guys, basically. So they thought, okay, I've got an idea. Let's build into the language a nicer way of accessing members of a pointer to a struct. So I'm going to call this print coffee ugly, and I'm going to call this print coffee nice. Nothing's changing here. I still accept a pointer to a coffee, except I don't need to dereference my struct and then access the name. I can use an arrow operator to say, just give me, this does both. It dereferences the pointer, then access the property. And, oops. And the syntax is it just reads a bit nicer. What have I done here? Oh, and then I need to call print coffee. And just to prove that they both work, I'm going to call both. I'm going to delete this one. Look at that. You didn't believe me. And we get the exact same output. So they're both equivalent. Do we all agree that that reads a bit more nicely than this? I do. I know you do. It all works exactly the same. Your whole worldview shift. Don't be so dramatic. Yeah, they are completely equivalent. So this dereferences the pointer, then accesses the member. The arrow operator dereferences the pointer and accesses the member. And so, oops, these are completely the same. How cool. All right, so any questions? Okay, Bubbling saying, can I explain what's happened again? So do we understand what was happening here, Bubbling? No, that's okay. All right, we'll explain this from scratch. Polkabro, why keep the two then? Why did the creators not just remove the ugly way? Well, because if you remove this, then there's no way to dereference a pointer. This is just using the building blocks of the language to say, take a pointer, dereference it, and access the member. So you can't just get rid of this whole ability, because then you couldn't dereference an integer or a double or a character. So let's break this down. We can pass structs to functions. We can throw structs around. The problem with doing that is that if we look over here, the problem with doing this is that we need to make a copy of the struct. The if statements you can pretty much ignore. So if you look, for example, here, Bubbling, are you happy with this with what we have here? We can pass the struct around. The problem with doing this is that we make a copy of the struct every time we want to pass it around. Copies are expensive because we need to ask for the memory. Okay, we're happy. If I want to avoid having to pass copies around, what can we do? There's only really one thing we can do, and that is to pass a pointer to the struct rather than a full copy of the struct itself. And that's what we're doing here. We make the struct all the same, except we pass the address of the struct. Are you happy with that as well, Bubbling? Okay, all happy. Then in our functions, we have to say, well, I'm not expecting a full struct. I'm just expecting a pointer to a struct. And that's what this asterisk means here. Asterisk means a pointer to the type. So now our function is accepting a pointer to the type. Okay, we should be happy still so far. We pass in an address, we accept an address. If I've got an address and I want to access the names or the members, so like the name or the price, I can't do mycoffee.price. Why? Because mycoffee is not a struct. What is it? It's a pointer. So what I need to do is dereference the pointer, which is done by using the asterisk. Then access the member. And that's all that this function is doing. What is within the procedure is the dereference of the address. Yeah, anytime you see this, it was dereferencing it every single time. So within the procedure, it's accepting a pointer, dereferencing it, and then accessing the property. Okay, awesome, you got that. And then all we did next was to say, and this is, I'm not singling you out, this is, if you're confused, there'll be lots of people confused. So this is all to say, this syntax is kind of annoying. You know, it's 3 characters to do it. That's really annoying. So the language designers of C said, well, because it's so common that we want to pass in a pointer to a struct, I'm going to create this arrow operator, and these do the exact same thing. So dereferences the pointer, gets the actual struct value, and then access the property. It's just a shortcut, absolutely right. What does dereference mean? Dereference means we have a reference or a pointer, and we dereference it. We get the value out of the address. Nikhil says, can we do the arrow pointer operator in the argument of print coffee nice function? No, because that wouldn't make much sense. If you just wanted if you wanted to do that, you would just pass in the name or the price, for example. You wouldn't pass in the whole, yeah, I don't think you can't do that. Okay, Gabe, any style deductions for using one or the other? You would never want to do this. I don't know if there's style deductions exactly. You would always do this. It reads much nicer. This, yep, Bonrick, is the arrow operator only mainly for structs? It's only for structs. I don't think it has a use anywhere else in the language. I could be wrong. Someone will let me know. It's only to access the member of a pointer to a struct. So Justin's saying, what's the advantage of using pointers? Why not leave it a struct? We did talk about that. Remember, if we're passing in the struct, we have to make a copy of the struct. That's really expensive. By passing the pointer, we don't need to make a copy of the struct. That's a lot cheaper. We're happy. Okay. Yeah, I don't think there's a need to do any of this in assignment 1. This is more for assignment 2. Yeah, thanks, Tammy. If we miss your question, let us know. Okay, okay, 45%, sorry, 95% are saying move on. You're pretty much happy or you're happy. That's fine. If you've got any last questions, please answer them. Ask them. Awesome. Always, so everyone, if you get it conceptually, but the syntax is not quite right, that's completely fine. That's good. The syntax will come. You will get the syntax. What's more important is that you understand it conceptually. Yeah, you'll just get the practice. So Matthew says, I thought the pointer already points to the value. How does dereferencing differ? You're right. This points to the value. But it doesn't change the fact that what we actually have is the pointer. What is my coffee right here? If I just had my coffee, what do I have? It's just a pointer. It's the memory address. It's a memory address. It's not a struct. So we need to get the value at the address. We need to follow it. And that's what dereferencing does. When exactly would we want to use the arrow operator? Would we want to use it every time we have a struct in a function procedure? Matthew, good question. Only if we're passing a pointer to the struct, not if we're just passing the struct. Yeah, I mean, really to drive it home, I can print f percent p. I can print my coffee here. And what you'll see is that that is my coffee. That is this line here. It's a pointer. It's just an address. So I can't do like this dot name. I mean, it just doesn't, it's not a struct. I've passed in a pointer to a struct. It's the hexadecimal address, exactly right. Exactly right. So I need to turn it into a value by dereferencing it and then getting the members. All right. Let's leave that there. Let's see what slides I've got. Okay, this is just showing it again. We can dereference it manually and then access the member, or we can just use the arrow operator. One more thing that's sort of worth pointing out. This gets even more complicated, or it's even better to use the arrows if you've got a struct of a struct. Like a struct and then a pointer to a struct. You'd have to do something like struct dot second struct, and then that whole thing would need to be dereferenced. And then you could do like dot name. Like it would just get worse and worse and worse. Do you know what I mean? Or so you could just do struct second struct, just to really drive home why the second version is more useful. Yeah, you can have, there's no reason you can't have layered. You get my point. Very good. That was very funny. Okay. Close without saving. Yeah, so you can keep chaining them. Whereas if you had to dereference them manually, you'd be really annoyed. Okay. Okay, all right, cool. Why don't we do the mid-lecture break now then? And now we're going to use these to do something even more cool. So, few-minute break, Kahoot, sure. Then we're introducing linked lists. How exciting. Make sure you recover over the break because this next stuff's going to get heavy. Not really, I'm joking. It's okay. All right, few minutes break, not too long today because we've got a lot to cover still, and then we'll do a quick Kahoot, 5 questions, and then we'll keep going. Spotify. I don't know who Milan is. Sounds good. Is he a maths lecturer? Is that what everyone's saying? I'll be honest, one of the problems with guest lectures that in the past that we've seen, I forgot you can rewind, Daniel, is that very few people come to the guest lectures it's a bit embarrassing. Like you get someone to come speak and there's like 10 people in the lecture because it's the break. So what I've been thinking of doing is rather than doing guest content in a particular course like 1511, we can do it sort of more broadly as like a podcast or something. It doesn't matter if it's like someone internal to the school, like Milano, something like that. But the problem is if we get someone external. If you all came, that would be fantastic. Which I know a lot of you still would, but... Homelander. Yeah, that's scary. All right, a few more minutes. No Homelander, please. Tammy and Patrick, I hope to see you in the game as well. I'm gonna go actually really quickly turn my kettle on. Okay, good to go. Let's start. Okay, I gotta Google this Milan guy. All right, I hope that the dereference operator in C is ampersand, asterisk, arrow, asterisk, bracket with a period. Yep, well done. Yeah, the kettle noise. Sorry. 39 of you got that. Well done, well done. Why is the Kahoot on my end started? Not sure. Yep, not much to say here. The asterisk is the dereference operator. What does the dereference operator do? It gets the value of that's being pointed to by a pointer. Okay, well done, Aiden. A nice, simple name. No games. The address of operator in C is... Oops. Well done. Yeah, 44 if you got that. Pretty simply, takes a variable and gets the address of the variable. Very nice. Aiden's still on top. It's a bit of an easier Kahoot today, I do admit. Okay, why do we want to pass in a pointer in a function? It uses less memory, it's faster, I can change the value in the function and propagate the change, or all of the above. Ooh, 19 said A, and then the rest of you said green. Look, if you put A, there's nothing wrong with it, you're correct. Interestingly, you could make an argument that it's not always faster, but I didn't say it's always faster. So if you have primitive data types, it's actually faster sometimes to make a copy to the data because the operations to dereference it can sometimes be slower depending on the size of the data type. Someone actually sent me an article recently. I got to dig it up. Maybe I can dig it up today, but pretty much it's faster because we typically pass pointers into larger values. And you can change the value in the function because you got a reference to the memory. Oh, we've lost Aiden. So sorry, RIP. True or false? Can I allocate struct memory on the heap? Ooh. True or false, 50-50. Okay, 39 said yes, 8 said no. Well done. If you, I mean, we can allocate anything we want. It's C. We can do whatever we want. RNG wasn't on your side. Okay, a few guesses here. It looks like. And then the final question. First is first. Excellent. Okay, here's a struct, an int age, a float. These are always hard. You got to have a hard question. A float weight, a car name 30. How much memory? I didn't even actually ask a question. How much memory will this struct require to be stored? Ooh. Oh, brutal. Brutal, 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 brutal. Only 5 of you put 66 bytes. Let's see. A lot of you said 12. So a lot of you said 8 bytes. I think what you thought there is that you would have a pointer to the struct. But I never said that, right? I just said if you've got the struct. Some of you said we can't tell because we don't know the size of the string, but we know the size because we know it's 30 times the size of a character. How many bytes does it take to store a character? 1 byte. So that's 30 bytes just there alone. I mean, so already if you just knew that, you know it's got to be more than 30. So it's probably not 32 because that's very low. So it's 66 bytes. 30 plus 4 plus 32, I believe. Let's see what happens here. Audrey coming on 3rd. Congratulations. Daniel coming on second, and then first, got it. Well, congratulations to first. AC and AR11 coming in fourth and fifth. Well done. Okay, hopefully that was a bit of fun. Because it's 30 bytes for the character. Should be 38? Yeah, I counted wrong. I counted wrong. Was it? Oh, shivers. I can't go back to the... I thought I counted 32 bits for the integer, but I counted 32 bytes, but it's 32 bits. But so does that mean the correct answer wasn't there? Yeah. Oops. This is the problem with whipping them up too quickly. Yeah, why did I do 32 bytes? I even thought like that's way too big for an integer. Lol. Yeah. Was there the correct answer? Was it actually there? No. Yeah, it's a huge integer. Well, so 18 of you put no answer. Maybe you're the real winners. What a stupid mistake. That's it. Anyway. All right. The points don't matter. Can't tell. Yeah, can't tell. You could also... Oh, you never know. It could be a really big integer. I never said what language it was. Okay. All right. Let's get back to it. Okay, let's skip this slide. We'll go back to it in a second. So, why did we talk about the pointers to structs? Yeah, I know, I really lost all my positive will, my goodwill. All right, don't worry, there'll be future Kahoots. All right, let's get serious for a second. So, there's a reason why we were talking about pointers to structs. It's because it's a core concept that lets us, my camera. So having a pointer to a struct is a really important concept and a building block for linked lists. Sorry, you're making me laugh. For linked lists. So before we talk about linked lists, let's talk about why we want them, why we need them, why they're useful, and what they are. So again, I always like to say this so far. Let's go back a few steps. If we want to store multiple elements, we pretty much can do that with an array. They all need to be the same data type, and it's a great data structure. I don't think anyone's arguing. We can do some cool things with it. But arrays actually have a pretty big limitation. And I've said here that I'm doing a demo, so let's do that. Now, I think I'm not going to write the whole program. So array problem o.c ampersand. All right, so I've written some code up earlier, but before I paste it, let me just describe it and you guys can tell me. Okay. If I've got some data in an array like this, and I want to, now I want something like this. I want to put a new value in my array. You're all reeling after the Kahoot. It's good to keep everyone on their toes. So I want to insert, let's say I just want to insert a new value into an array. Can you tell me, well, first of all, how do I do that? How do I do that with this? Can I do it? You don't? But I want to. I need to. Dang says find the index, but if I find the index, what do? I can't extend it. I can't make it longer. I need to make a new one. There's no append. This is C, Bonrick. We don't get nice things like that. Okay, we can't. Well, you got to change the array. That's right. We've come up to a problem here. This is a static length array. It's always going to have 5 elements. I know you know, Bonrick. It's always going to have 5 elements. We can't extend this array. It's static. Okay. But did we talk about dynamic arrays? Do you remember those? Remember dynamic arrays? With malloc? So we could do int dynamic array equals malloc the size of dynamic array times 5. I could make an array on the heap, and then if I wanted to increase the size of it, I could do that. Remember? So we had realloc. Oops. I've cut my line off. Something like that. I could do this, right? So I could, what did I do? So, okay, it's all right. I'm not really planning on compiling this. So I could do this, right? I could extend the size of my dynamic array. Agreed? This is coming back to us. But dynamic array extended is still going to be 1, 2, 3, 4, 5, and then some empty spot here. But I wanted my new value to go in here, like in between here. So what would I need to do? How could I do this? I mean, you might not know, but if you just look at it, yeah, I mean, exactly right, Bonrick. We need to move the 4 over here. Move this, sorry, the 5. Move this 4 over here. And now I have the spot that I can put the 3 in. Agreed? Now, turns out, here's the program that does that. So I wrote this at some point last night or something like that. And it's pretty simple, pretty similar to what we had. So we had this data array here. We had the dynamic array with 5 elements. I put some data in the array. I printed out, so this is just printed out, put the data in, print it out. And here is the actual extension where I put, I do that, what we just spoke about. I shift those values over. So let's take a look at it. And again, my problem is probably the fact that I call that array something so large. So I get a new array. I reallocate the memory from the previous array. In fact, that should be like this here. But they would both work. So I reallocate it. So this gives us the same data in the new larger slot. Then I have to start at the top of the array. So I have to start I at 6, loop downwards, copy the data from the next door element over into my current element and loop down only until I get to 3, because 3 is the index at which I want to change it. Then I set my new index there and I print it out. And if we run this, DCC array problemo, I didn't save it. I really hate that. Array program. Okay, I have an unused variable. That's not a problem. That's just this one up here that I was using to demonstrate. If I run the program, oh, I actually get a error. Malloc after free? Oh, this needs to be using dynamic array extended, not dynamic array. oops, and here. I think that's what that was. Cool. So here I have that first set of data, 0, 1, 2, 3, 4. I did the reallocation and I get 0, 1, 2, 3, 3, 4. So it's possible, right? We've done it. But I think you can all agree this program is a lot of work. Yeah, it's a lot of work. Not only is it a lot of work to write this code, but think about like how many memory allocations we've done. We had to do this memory allocation here. Then we had to do another memory allocation here. Then we had to move all the data. Yeah, this is not what arrays are good for, is essentially the takeaway position here. Now, I'm not asking you to understand this program just, because I just pasted it in. But the point is they have a problem. The problem is when you want to insert data and you've got a full array, you need to make it bigger. You need to do a malloc, you need to move it all, you need to shift it all. Yeah, let me just do this. We need to shift all the data, and it's not really what arrays are for. But so what if we did want more flexibility? What if I had a data structure, I had a program, I had a problem where what I wanted to do was inserting all the time. It's just, I needed to do it a lot. Arrays would be quite annoying to do that. Who can tell me why arrays aren't good at that? If you can remember this word, I used it when I introduced arrays in the past. What about arrays is that makes them difficult to do this? It's not that they're static, because I showed it with dynamic arrays. It's not really that they're fixed size. Daniel, arrays are stored in one place with a fixed amount of memory. I think you're getting on the right track. Okay, Gabe, congratulations. The memory is contiguously allocated. That's the problem. The problem is all the memory is in one seamless block. There we go, I'll do that. So if I want to move the data around, I need to make a copy where I can get some more room and do the shuffling. Now, someone's asked, why can't the data, why don't we just make our array bigger? And then we don't need to do a reallocation, right? You can just do the shuffle. Well, you can imagine if the array was huge, it's a lot of shuffling. Agreed? We gotta still do a lot of stuff. We have to move all the data. What if I wanted to do multiple things? Oh, I gotta do it all multiple times. Yeah, it's easy to write. We just call the function, but it's a lot of work. So attaching another element of memory is problematic because the memory is originally stored all together 100%. So I've got to move it around, make it bigger, shift them down, put it in. It's a lot of work. That's not what we want to do. So this is what linked lists are for. So a linked list, you can imagine it, rather than one block of memory, it's a chain of smaller blocks of memory. And the chain nodes, right, the things that are hooked up on the chain are what we call nodes. So what is a node? Typically, it's just a struct. It's just a struct. We've done structs. We're happy with structs. All right, this is good, Jake. I know what you're thinking. All right, I know structs. I'm happy. The struct has some data. That's easy. It's just an integer. And it's got this thing. And this is the magic. This is the magic. But there's nothing crazy here. It's saying my struct stores some data. This could be an integer. It could be something else. It could be another struct. It could be whatever. And it stores a pointer to another struct, another node. Remember the asterisk means a pointer. Whoops. So you can sort of, I need a whiteboard. Oops. And then how do I need some text. Give me some text. So data pointer. Put that here as well. So what we're saying is this node, this struct, oh, let's not do that, has some data, so it could be like the number 3, and it's got a pointer to another struct. So what is a pointer? It's a memory address. Remember, this is all in memory. Our memory is a grid. And so it's saying, well, okay, store the pointer to this memory address. This has some different data. This has a different pointer that stores a different address with some, more data. And then this has another pointer that goes somewhere else. This is all in the heap. That's correct. Good point. But why is this awesome? Because, whoops. Can this go away? Oh my God. Okay. Yeah, this is... Anyway, okay, this is not working well. Because if I wanted to insert this element here, this has data. I don't know what I've done, and then the pointer. If I want to insert the data, for example, in the middle of here, what do I need to do? Well, I just... why is it grouping it? Okay. I just cancel... I remove that pointer. I then say this points to this box, this points to this box, and I've inserted the node. With just 2 operations. Okay, there's a lot of chats here at the moment. How does the first pointer know where to point to? We tell it how to do everything. We can add or remove elements just by changing the pointers, 100%. When you call the first one, then all are accessed. Not quite, but we'll talk through that. How do we know the address? We'll get it when we create it. So is all data that is linked to a pointer in the heap? The pointers can be at any memory address on the heap or the stack. Next is the name of the next node, yep. Does that mean make a cycle? Yes, absolutely. I think that's what you're saying. You just change one pointer. Okay, and it becomes linear access memory. They can be arranged in totally different areas instead of a line. That's right. So again, why is this useful? Because when we have large arrays, if we want to insert a value, it's really expensive. With linked lists, it's really cheap. So let's talk about the way we actually sort of build this concretely. So our node is just a struct with the data and a pointer to yet another struct. So some data type and then a pointer to the next node, which happens to have some data and another pointer. So here's a nicer attempt at what I was trying to do. We create the linked lists by having many nodes with each struct pointer pointing to the location of memory of the next struct. You've got to change 2 pointers to add a node, AR11, because you've got to change the previous one and the next one. But yeah, pretty much. So you can imagine, now, remember, yeah, I could have just shown you this. Good point. So we spoke about arrays being contiguous, one big block of memory. So if you think about an array, an array needs this big block. And all the data needs to fit in it sequentially. But with linked lists, it's broken up. That's why they're called linked. They're linked by the pointer. That's exactly right. Bubbly and good point. And our linked lists, just like our arrays, can be really, really big. It's like this is a cute little point. It's like a scavenger hunt. You have some data, you've got a pointer. Okay, let me follow the pointer. Oh, more data. Oh, another pointer. Let me follow it. Oh, and you can rearrange the chain as we need to. So how do I know what my linked list is? How do I know where it starts? Well, if we have a pointer to the first node in the chain, we can just follow the next nodes to sequentially access all of my nodes. So basically what I do is I have a pointer to the first node that is my linked list. So like arrays, when we have a pointer to an array, we have the whole array. All I need is a pointer to the linked list and I've got the whole linked list. I can't read all the data yet, but I have it. So a pointer to the first node isn't a node itself, right? So I just have the memory address of the first node. There's no data. It's not a struct, but it's just the memory address that points to the first node. Yeah. How do I know when I'm at the end of my linked list? Well, the final node points to null. We've seen null a few times in our programs. Null is a special pointer address. So actually, I mean, it's kind of cool to think about, but basically in our memory, there's always a special memory address called null that our programs know what it means. So if we point to it, it just means like, oh, I know I've got null here. There's no more. Whoops. So if we have a pointer to null, that means we're at the end of our linked list. There's no more nodes. So let's look at an example here with some actual sort of values. So we have the head of our linked list. It's a pointer to this memory address. We can follow 0xff0. We get the memory address that starts this entire struct. It's got some data, the value 1, and another memory address that's stored in as the next pointer. So if we dereference that pointer, what do we get? We get another piece of memory at A44 that stores this node with the data, the value 3. We can follow that again, 3B4, we go to 3B4. If I look at its next pointer, oh, it points to null, that's my entire linked list. Valerie you've obviously seen this stuff before. You're 100% correct. We save time for rearrangement. It's linear time, but the cost of access time, which does, so it is slower to go through our linked lists rather than our arrays. So there's always pros and cons to data structures. Okay. So what are the building blocks? What do we actually need to do to make a linked list? It's pretty simple. We have to define the struct for the node. We have to tell the struct that it's got some data and it's got a pointer to another struct. We need a pointer that keeps track of where the start of the list is. And we need some ways to create nodes and connect them together. So let's say we wanted to create a linked list with the data 5, then 3, then 1. First of all, we'd create our first node to start the list. We need a pointer to keep track of where the start of the list is. And then our node will just by default point to null because we have nowhere else to point to at this point. Then I can just create a second node and I tell my first node to point to the address of the second node. And then we do that one more time. We take the last element. We, instead of pointing to null, point to our new struct and go off. Okay. So let's jump into the editor. Oh, hopefully I didn't cut too much off. So Joe's says, quick question. Is this still an array or we're using it to replace array? It's not a replacement to an array. Arrays will never go away. Arrays are incredibly useful. I use arrays more than I use linked lists. They both have pros and cons. Arrays are really good at random access. So I can just access the 5th element, the 10th element, the 100th element, because I can just do my array bracket 100. That's what arrays are good for. Linked lists are really good for if I want to change the order and insert new nodes at any time. However, they're slower to read all the values, and they're not random access. So it's pros and cons. It's pros and cons. Okay. Let's clear this. gedit intro to linked list.c. Oops. And the ampersand, int main void return 0. It's a proper program, so let's go a linked list demo. This would be a good, we have we have about 20 minutes left in the lecture. I think this would be a good point for you to follow along at home. So I'll remind me and I'll bring my speed down a little bit so that you can follow along. So open up your editor, quickly make a file, if you are able to, of course, and we'll do that. So some questions while I wait. Generally, our arrays are preferred, especially if we don't anticipate changing the elements often. Look, it depends on what we're doing and how important performance is. Polkabra, interesting question. When you have an array, can you convert it into a linked list in the program? There's no way that I know of in the standard C library to do that. However, there's nothing stopping you from writing a function that could do that. A pretty expensive operation though. You have to traverse each element of the linked list, get the data out, have some way to append that. Yeah, it's not too bad. You could do it. Can we have an example of a practical application? Yes, you can. Linked lists are extremely practical. I think one example, now I don't know if this is actually how browsers implement forward and backwards, but if you think about a browser, what is going on? If you think about a browser, you can think as the backwards and forwards as being like a linked list-esque structure where you store the URL of the previous one and the URL of the next one, and that's the data, and the pointer is sort of where you would point to. Linked lists are also the building blocks of trees, which then open up an entire new practical set of use cases. We can also just quickly Google practical use cases of linked lists. Yeah, so they're building blocks for a lot of other data structures, which, I mean, probably won't make you feel nice. But basically the answer is any time at which you are inserting new elements in the middle of the structure often is when they're super useful. People are saying queues a lot, but again, you probably aren't going to appreciate that just yet either. Okay. All right, so that's enough time. Okay. So let's go linked list demo, Jake Renzella, 2020, 22T2. Okay. So first of all, let's go include standard io.h and include, we'll include the standard library.h because we'll be needing to do some things from there. Yeah, Daniel Berry, exactly right. A tree is a linked list, except it's more than one pointer in the struct. Okay, all linked lists we typically have a struct to store them. The struct is going to be called a node. In the node, we're going to have some data or a payload. It could, in this case, we're just going to do an integer. And then, excuse me, and then we need a way to store the next struct. So another node, and except it's not going to be a full copy of the node, it's just going to be a pointer. So we have the asterisk there, and I'm just going to call that next. I'm out of tea, even though I boiled the kettle. That kettle was a waste of time. Yeah, this is just the beginning, as Patrick is saying. All right. Okay, so we've defined this struct. I'm not going to forget the semicolon this time. We've defined this node. A node has some data, and it has a pointer to another node. In main, well, okay, before we do that, what we want to have is a function that can create a node. Because we're going to be creating lots of nodes. If we're going to do something lots of times, we want a function to do it. So if we're going to have a function that creates a node, we need to return a struct node, and it's going to return a pointer to a node, so not a node itself. We're going to call it create node. It's going to accept a few pieces of data. It needs the data itself, and it needs the memory address of the next node. So let's annotate this a bit. This function creates a new node from the node struct. It returns a pointer to a node, and it accepts as the parameters an int data and the memory. That's not really a nice way of doing it. And the memory address of the node. So it's not the next node, actually, it's the current node. Parameters. Okay. So, question. If I just make a node here, what will happen when the function ends? Yeah, exactly right. It'll die. So we want our linked list nodes all to be on the heap. If we want the data to be on the heap, we need to use malloc. Exactly right. So pretty simply, I'm going to make the node. So struct node, my new node, is going to equal, and I'm going to do a malloc, a call to malloc, right? And I need to tell it how much data to store, and how much data am I going to store? The amount of data needed to store a struct node, or we can just give it new node. So either or will be enough data to store a struct node. So you could do this, or you could do size of a struct node. So make a node on the heap with enough data for a node. Okay. We can't just return it. We need to set some of the, values of the property of the node. So there's two things in my node. So there's two things I need to create. I've got this new node. Now I have an interesting question for all of you. New node. What is new node right here? Very good, Matthew. Yes, very, very good. It's a pointer to a struct. Okay, so if I've got a pointer to a struct and I want to access the data, what do I use? Very good. I'm so glad no one just said struct. It's a pointer to a struct. Yes, exactly right. So we can use our brand new arrow operator to say dereference the pointer, get the struct, and then access the data field. And what are we going to assign it? We could assign it a value, something like this, but we're already passing in that data as an integer. So I'm just going to assign it to data. There we go. Then we also have this new node, and we're going to say that the next address is going to be equal to this address. Now, next is a pointer, address is a pointer, so we can just assign it like that, and we're happy. So this is the next address there, and then I can just return new node. And once again, it's returning a pointer to a node. Okay, cool. And that is it. That is the function required, blah, 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 to create a new node on the heap. We're happy. Okay, let's actually play around with it. So in main, I want to have a variable that stores my pointer to the first node. Yep, already did that, Nicholas. That's fine. Okay, wouldn't next equals null? Good point, Gabe. You're going to see something cool in a moment. But you're very good thinking. Very, very good. Okay, we have this main here. I want a pointer to a node. Well, so I'll just make one. Struct node, and I'm going to call it the head pointer. So declare a pointer to a node. That's all it is. It's not an actual node itself. It's just a pointer to one. Then I can say that that head pointer is going to be equal to the result of calling create node with some data. Let's give it the data 1, right? The value 1 as the data. That's this data here. Now, who was that? Gabe. Do I have a next pointer? I've only got one node. Like I've called create node once. I'm storing it here. I don't have anything else. You're saying we have one on line 12? Not quite. This is just the prototype. Yeah, not yet. All right, so I've got nothing to point to. What do I do? Do I cry? No, I'll say just point to nothing. Don't point to anything. So it will pass in null here and assign next to be null. Nikhil says, huh? Create a node with the data 1 and point to the null pointer. Remember, in C, null is actually a pointer to a special piece of memory that stores null. Okay, everyone's going, oh no, but how do we change the value to pointer? Don't worry, we can do that. We can do that, no problem. Because remember, right, I've got this pointer here. This is now a node, so my head pointer, I can dereference the node and get the next, and I can change it. this is just setting it up, right? I can still change it later. So why don't we do that? And this is where, okay, if you can follow along here, you're in really good, you're in a really good position. Yeah, that's right. We've only just initialized it. So what we have here, in fact, I think it is really worth having a whiteboard for this. That can go away for now. I don't think my iPad's got any battery. That's fine. New whiteboard. I'm just going to draw it out. So what have I got here? I've got a pointer. So I've got some memory. I've got a pointer here called head pointer. And it stores a pointer. Now I've created a node with the data 1 and, oh god, this is not good, is it? And pointing to, no, that looks awful. And pointing to null. Yeah. Exactly. Okay, now what I want to do is I do want to link up some more nodes. So I can say, well, my head pointer is now going to be storing, I'll create another node with the data 2, and this one will then point to the previous head pointer, like this. Okay, so what's happened here? So this is what we have as of line 20. Line 21, what do we do? We create another node. Well, first of all, we get the value of head pointer. Head pointer is now pointing to this at this point here. So we can call this like 0x1. I know this is really impossible to see. Yeah, that's right. It's going to go backwards, Nickel. Yeah, very good. Then I make another node. It could be down here. I store 2. And it's pointing to this value as the next. So 0x1. So this points over to here. And then I'm assigning head pointer to point to not here anymore, right? Because I'm changing it, but to point to here. Okay, we've just constructed a node. And if we really want to be nice, we can actually do this backwards so that this is actually three, then 2. Do you see that? I know it's a bit hard to understand. I completely get it. Is this code actually available? I can't remember. Let's do it one more time. I'm just going to copy it down. 1, and that's it actually. Nothing else changes. Let's just draw it out again. Okay, so anyway, that's really annoying. We make a new create node. So we're making a new node down here. It stores the value 1 in data. It's going to point to head. What does head point to? Head points to the memory address that stores this node here. So this is going to point to this one over here. Then we assign the head pointer to no longer point to where it was pointing to. We lose that. But to instead point to the result of calling create node, which is going to be this address. And so you can see if we were to go through, we have address 1, address 2, then address 3. Data 1, data 2, data 3. And that's it. We've made a linked list. Damn. We just made a linked list. Now, compiler didn't like this. Okay, that's a good idea. DCC intro to linked list -o to program. Oh, wrecked. That worked for me. Now it's not going to do anything. Oh, I'm getting a runtime error. That might be what you were talking about there. I wonder actually if it's because, should that actually be struct node there? I thought that was okay, but I might be wrong. No, that's what it was. Okay, apologies. There we go. You have to do the struct node. I guess it would be the pointer maybe in that case, because it's not a data type. So that's the issue there. Yeah, someone asked, how do we insert between elements in a linked list? We will get to that. I'm going to put struct node there. Go away. But we've done it. We made a linked list. I mean, that's sort of. What if you do a new node? Yeah, that would be new. Interesting. Oh, that also works. Yeah, well done. I think that should work. But you could leave it at that to be safe. Good pick, Daniel. Okay. I think that's where we're going to leave it today. It's a nice spot to leave it. Yeah, the cliffhanger, and it is a bit of a cliffhanger actually, because next week is the midterm break. We actually have made a linked list. However, we're not doing anything with it, and we haven't looked at how we can insert new elements and things like that. So I think this is a good spot to leave it. Like Joe is saying, he just needs to digest. Can we print the list? You can print the list. I think this is a really nice spot to leave it because we've covered a lot today. In the next lecture in week 7, what we'll be doing is basically printing the list. So this is a classic cliffhanger, but I think it's a really good spot to leave it. Maybe what you could do if you're really keen on this stuff, make the function that can print a single node. That would be a really good sort of activity. So I'll leave you with that. If you are keen and happy with the content, try yourself to make a function which prints the data in a node. It shouldn't be too bad. Okay. Top 10 anime cliffhangers. Yeah, exactly right. Someone asked a question about functions, and now I've lost it. Could you do a rundown of the function again? I get the part inside of main. Okay, this function down here. It must be what you're talking about. Okay. We want our nodes. This will be the last sort of thing we discuss, but if you need to head off, technically the lecture is sort of wrapping up. But and I just want to say one thing before we talk about the function. A couple things. Linked lists are the culmination of a lot of tricky concepts: pointers, structs, functions. So it will take time to get your head around it. Practice. Draw it. Whiteboard it. You will get it, but be kind to yourself because it's not something that will just come like variables, for example. That's the first thing. The second thing I want you to think about is a little bit more sort of not philosophical, but theoretical at least. I think it's really cool is what I'm trying to say. When we made arrays were sort of built into C, right? Do you all agree? You had special syntax for the square brackets. You could get the index. They were built into the language. Linked lists, I mean, we've created from... There is no linked list in C. We've created this ourselves. This is data structures now. This is really cool. we're putting together concepts to build structures that store and manipulate data really well. I mean, this is what it means to be a computer scientist. So this is all from scratch. That's right. We're just using the building blocks that the language gives us to create this linked list data structure. So I just want you to take a moment to appreciate how cool that is. Okay, let's run through the function one more time, and then that's the end of the lecture. If we want to create nodes to chain together the linked list, we need a function that can create a node. Okay, what needs to go into the node? The data and where the node will point to, which is just an address of another node. Are we happy so far on that? I can't remember who I'm talking to. Yep. Okay, cool. Okay, yeah, Matthew, that's right. All right, so we're happy there. Next, we make the node on the heap. If we want data on the heap, we call malloc. We tell malloc, how much data do I need? I need enough data to store the size of a node struct. Okay? So this will just get me on the heap enough data to store a node. That's what this is doing. And then it returns the address of it. And we assign that address to new node. Then I initialize the data, and I initialize the address to be the address that I passed in, and then I return it. What am I returning? I'm returning the address of the node where it was defined when malloc was called. That gets returned here, that I assign to that. If it's the first time I'm calling it, for example, the head pointer. So what's sort of interesting here is that we're constructing the linked list node backwards. Why does it make sense to construct the linked list node in backwards order? Because the last node won't point to anything. It will point to null. Then I know what the second node should point to, and then I know what the first node should point to. So constructing it backwards makes a bit of sense in this case, if we can. Sometimes we can't, and we'll look at that in the future. And that's it. That's where we're leaving it. Not too much code, but in memory here, we have a linked list. Very cool. Thank you all so much. I'm really impressed, actually, at how well at least those of you who are talking, have followed it. If you're not one of the people talking and you feel like, why don't I get this? This isn't for me, blah, 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 blah. Relax. Like I said, this is the culmination of a few different tricky concepts. You will get there. Programming is interesting and it's hard because it's theoretically and conceptually heavy, and it's a practical skill. So you need to do both. Okay. Thank you, Weena. Appreciate you. Appreciate everyone. Have a good flex week. I'll be in touch if we run some bonus stuff next week. Next is a pointer that can point to a struct. That's right. Thank you all for your time. Good luck with the labs. Get on top of stuff. Look after yourselves. Thank you, Tammy. Thank you, Patrick. Am I missing anything? I don't think so. Have a good one. No more 2-hour Kahoots. No. See ya.